Okay, I think maybe you can start. So, one of the questions that came up last time was uh, in the so how is the matching between HQET and QCD done? In particular, there were some questions about how does this you start with this current, which is heavy light current, Q, let's say Q gamma mu Q. And then we've seen that this matches to, this is in the QCD, and in HQET, this matches to some, not just Q gamma mu H, but it also has some contribution from Q bar gamma V mu. So the question was, how does this come, this mixing come, and also how does the matching work in general? I'll give you some steps, and then you can complete the details. So what is matching? So you want to match certain certain operator expectation value. Let's say, for example, some physical scattering matrix element. You want to say it should be the same in QCD and in HQET. So my current is Q bar gamma mu Q, but this matrix element, well, so a couple of things. There'll be this residue because I want LSC to hold. So therefore, I have this two factors of field renormalization, wave functional renormalization that comes in. So that is one thing. Now, if I just, at tree level, they're obviously just one, but we are matching to one loop level, so that's why I have to keep them. Now, once again, at tree level, this expectation will be just gamma mu, simply because you contract this Q with Q, and this Q with Q bar, and I simply get gamma mu, that's all. Okay? Maybe there's one more thing I'll say. You have to choose some external state to do the matching. So I've taken this light Q to have zero momentum, zero mass. This heavy Q has a P mu, which is mv mu, so on shell. If I had chosen to do the matching at some momentum, external momentum P for the Q light quark also, then of course there are more combinations I can have, right? So all vectors that satisfy the quantum numbers can arise. So I can have gamma mu's, V mu's. If there's an external K mu for the light, that can also come in. But I've set the external to zero, so that's why only these two appear. Okay. So on the HQET side, I should add all the currents, so Q bar gamma IH, such that these two can be equal. Okay. So the question is that how do I see at one loop these terms are generated? And really in QCD, the calculation is straightforward. So okay. So the first loop correction is this plus counter terms. Okay. So this diagram you've made several times. So let's say gamma mu, this is gamma mu, so gamma mu, gamma mu. So let me call this piece delta. from here. And there's this loop, these vertices, which will simply give me some color factors into I into pi hat. Okay, so that's basically the diagram. And M is M quark, heavy quark, light quark is massless. Okay, so this is what you have to compute. So you should compute it in detail at home. The one thing that I'll do is clarify one piece of the structure, which is that you do it using the usual Feynman trick, dx1, dx2, yep. And in the numerator, after doing the usual Feynman trick, you'll get pieces which are like gamma nu, okay. So the thing I wanted to highlight is that this term, of course, can only give you something which is like gamma mu, because this only involves Q, and Q is integrated over. There's no, after you do all these usual gamma anti-commutations, you just get a gamma. Q slash just gives you Q square. So this is the term which can give you V mu. And the way it works is after doing the commutation, you will have situations, you try to move all the p's to the right-hand side. So for example, if you have x1, 1 minus x1, gamma mu, p slash. So this has to act on V later on. So later on when it acts on P, there's a property of V, sorry, this is U, which when it acts on P, so when P slash acts on U, it gives you something simple. Can you try to remember what it was? V, yeah, yeah. So perfect. I mean, yeah, right. Sorry. Yeah, in fact, it will just give you M. So the idea is P slash times U equals to M. And the reason is the U already has the projection 1 plus V slash by 2. So this just gives you. Okay, so that's really it. So once you then do the usual dim reg regularization, you can evaluate this integral and here. So just this part of the diagram, W mu, simply turns out to be it's a remarkably simple answer, actually. To that, now you have to add these counter terms and then multiply by R's to get the matching coefficient. So I think that you can do, and I'll now just give you the final answer. That so only two contribute here. So C1 corresponds to Q bar gamma mu H, and C2 corresponds, C2 is the Wilson coefficient associated with Q bar H times V. And P1 turns out to be equals to okay. So few things to note. First of all, there are no UV divergences, of course, in the matching. And that has to happen because the way you chose all these counter terms is that the UV part has to cancel out. So there can't be any UV 1 upon epsilon c in this, in the matching. One can worry about, can there be infrared 1 upon epsilons? Because the counter terms only cancel the UV divergences. They don't cancel the IR divergences. And in fact, both in HQET side and in QCD side, there will be, oops. This reminds me of one episode where Hitoshi, I think, I was in a conference. Hitoshi got a phone call when he was giving a talk, and then he took the call and went out. I think you were there also that time. Yeah. And he was gone for like 5-10 minutes. Oh. Interesting. So this was not, definitely not that. Yeah. So, so you could worry that there could be IR divergences. And the point is that the IR in both QCD and HQET are the same by construction because at the low energy, both are the same theories. So, in fact, the 1 upon epsilons that you get from IR in both of them, if they don't cancel, then you made a mistake, basically. Okay, so that's those are 2 points about divergences. And finally, you can see that the logs of mu by MQ come in. So you have to do this matching at a scale, which is at order mu of the order of NQ, otherwise you'll get large logs. Yeah. Okay, so I think a good exercise to do is, I think this is not straightforward, so I'm not giving this for the tutorial, but I think this vertex you have seen in your QFT courses. When you calculated them, you probably put in a mass for the for this photon or gluon. So in fact, this I made it a photon, but this should be a gluon. So you put some finite mass so that you get a fine IR safe result. Okay. What is worth trying to do is now just don't do that. Just calculate it in DIMREG, and there'll be some cancellation between the UV and IR divergences, but you'll get a nice final result. And actually, you can simply show this very, very quickly. Yeah. So, good homework exercise. Okay.
A better one of filling the DIMREG, write it down in terms of epsilon IR and epsilon UV. Absorb UV counter term from which we determine what terms you need to match in the IR with matching the epsilon IR. That's basically.
Yeah, right. Yeah, in fact, that's one way to find the epsilon UV. Yeah. So, okay. So, if you have any questions. Yeah, sounds good.
No. Okay. So my goal is to fill up some things that we saw yesterday. We saw the PNRQED Lagrangian in terms of this paired field phi. Okay, Rishi wrote in the end. I would rather express it in terms of a more gauge invariant form, which is something called as gauge singlet, and then show a simple example to something like Rayleigh scattering that we study in electromagnetism. Why sky is blue as an application of PNRQED. So, so yesterday, Rishi had this thing. Plus for chi-C dagger. So chi-C, if you remember, was the conjugate field, which was defined as I sigma 2 chi star. Just let me, yeah, minus I sigma 2 chi star. And it was the same Lagrangian going from E to minus E. And then what Rishi did was to introduce a paired field phi and project this NRQED Lagrangian onto PNRQED using this paired field phi. So paired field was D3 X1, D3 X2, phi ij, psi dagger I, chi dagger Cj, vacuum. There is X1 and X2. And obviously this is function of X1. Now to write the Lagrangian in this, you basically take this phi, compute the expectation value of this, and you will have a Lagrangian now written in terms of this paired operator. The paired operator is like analogous to the thing that we have seen earlier. Yeah. Which was, I'll not write the full Lagrangian, but just some terms that are important to express, to see the dipole term. And this is just phi dagger R. These are three vectors, I del 0 minus E R dot del A0 RT phi. So there are more terms that I'm not writing right now, which is not relevant for this purpose of this part. I have done multiple expansion. Note that my gluon field here is only function of the center of mass coordinate and not the function of the relative coordinate. The center of mass coordinate goes like 1 by m alpha square. Yeah. Whereas relative coordinate goes like 1 by m alpha. Okay, so now the goal is to express this PNRQED Lagrangian here in the box. No, the phi will, that's x1, x2. That has both the coordinates. So the heavy quark field does have the relative coordinate piece, but your gluon fields are all expanded out. So so phi is a paired field that is dependent on both x1, x2, which means this is a paired field that will depend on both relative coordinate and center of mass coordinate. But the gluon field being, because you want to force the ultrasoft degree of freedom, you want to integrate out all the dependence on the relative coordinate. And so you multiple expand the gluon fields. This is the peculiarity in this PNRQED, basically. Yeah. So let me define a field redefinition. So I want to express this in terms of a gauge singlet such that my NRQ, such that I can have, I can manifest the gauge invariance in the multiple expansion. So field redefinition, I define a singlet field, which is I will define what this business is, or sorry, so this is phi RRT 01 DS. Oh, thank you. Does anybody connect it what this quantity is? This is basically something connecting a charged particle E plus, E minus. Let's say this is at R minus R half by 2. This is at R plus R half by 2 at time t. Because I have already defined my paired field, which is containing both E plus E minus. And this is some line connecting from E plus to E minus. Good. That's the Wilson line. It's the Wilson line connecting from R minus, R. This is the final position. This is the initial position and time t. Okay. Now we know what is the gauge transformation of the Wilson line is. The Wilson line basically, in general, transforms as some e raised to I. So, yeah. Okay. Let me just make it xy, then my x is R plus R half by 2 and y is R minus R half by 2. So under gauge transformation, or the ultrasoft gauge transformation or the U1 gauge transformation, the Wilson line will go like, will transform to some e raised to minus I e lambda x w xy t e raised to I e lambda y. Okay, so it's like u inverse. My phi field, which is defined as some R, capital R and T, is really proportional to some, so look at this picture basically here. So I have a particle at position r plus r half by 2, anti-particle at position r minus r half by 2. And this transforms as some e raised to minus IE lambda x. So x is my this phi field e raised to IE lambda y. Okay. So my particle transforms, I mean, you have to use the fact that psi transforms as e raised to minus IE lambda x psi. Psi c would transform as replacing e with minus e, that is what we wrote. So e raised to IE lambda y psi y. Okay, this is the point. This is what you are. This is what we are trying to explain. So now you just see that when I wrote this relation, looking at the gauge transformation of the field phi and the gauge transformation of the W, it directly tells me that the S is not going to transform. It's a gauge singlet. Yes, everybody is following. Clear? So this is the singlet. This is the singlet field under gauge transformations, and so S is basically gauge singlet. And because it is a gauge singlet, I cannot have anything else in, I do not have any color degrees of freedom in QED. So that's because I have defined once my gauge singlet, it's easy to express everything my Lagrangian now in terms of this gauge singlet field. That will manifest my gauge invariance. And to do to re-express this Lagrangian in terms of now singlet field, you also have to do a multiple expansion of the Wilson line, okay? Because there is this gluon field that is depending on both small capital R, the center of mass coordinate, and the relative coordinate. So I just express my gluon field as, or the Wilson line as 1 plus IE R dot A RP, so capital R, plus some order R square. I will only focus on the order R term in the PNRQED Lagrangian. I leave order R square to you to do. So the first, what is the first term that we have, which is phi dagger I del 0 phi. So phi dagger I del 0 phi would go as 1 minus IE R dot A. So A now depends only on center of mass coordinate. Let me just keep on writing so that it's clear. So 1 plus IE R dot A plus order R square. Fine. I did nothing else. I just expanded my Wilson line and substituted this relation. Expanded the Wilson line and just substituted this relation. There is a singlet field, sorry. So S dagger S. And this immediately allows you to express something in terms of this. This is S dagger I del 0 S minus S dagger E dot ER dot del 0 A S plus order R square. So when this covariant, when this derivative acts on this on the right hand side, it acts both on A and S. The term corresponding to S is cancelled by the one of the terms coming from here. And so you're only left with this piece out, and then there are order R square term. Okay, it's clear. So note that this del 0 will act both on A and S. You have to do the multiplicative, whatever the differentiation rule. And then the other term that I have there, phi dagger, ER dot del A0 phi, will similarly, if you just keep the order R term, you just have to do it as, just take the expression instead of going through all the steps, plus order R square. So let me mark term 1. So this is my, let's say 1, and this is my 2. I will focus on these two terms for the time being because, so let me do 1 plus 2. And that directly is S dagger. What do you expect? Yeah, maybe that's a good point. What do you expect from this if you do 1 plus 2? So don't worry about this term. Okay, this is some usual time derivative term. You should take this and see what you get. No, where is the covariant derivative? No, you won't get a covariant derivative. I mean, okay, let me maybe write the form, then people can probably have a look at it. What is this term? Or even if it is not clear, let me pull out the R factor then. So now what is this term? What is it? It's electric field. So you really get the dipole term out, okay? Which is talking about the polarization of an atom due to electric dipole. Now I showed you how you get the electric dipole. The next question is, what do you expect will happen at 1 over m? Which term will appear up? Is the question clear? This is an electric dipole, yeah. So here there was this D naught. This will act here as well as here. So the action of D0 on S will be cancelled by if you take, let me see, yeah. So if you take, but that is cancelled, that is what I'm saying. It's cancelled. So this D0 acts on A, D0 acts on S. What you are considering is S dagger, IER dot A, del 0 S. But it will be the same term that will also come from D0 acting on, yeah, and it will cancel. That's the point. And you are only left with this term. And now if you massage, you get the electric dipole. What is the next term that you will expect? Okay. No, there is no quadrupole. Let's not go to quadrupole. And what is the form of the magnetic dipole? Yeah, okay, good. Then what is the sigma? I have a quark and anti-quark. Think like I have a magnetic field in Z direction. I have a particle, I have a E plus and E minus. I want to write a magnetic dipole term. Think that B is in Z direction, the magnetic field is in Z direction. What is the form that will come up? So take that the spin of particle is S1, spin of antiparticle or the spin of electron is S1. So let me define the quantity. This is S1, this is S2. Consider that I have a B field in Z direction. So BZ. Now, what is the form that you would expect in terms of S1, S2? What is the Hamiltonian of a magnetic dipole? You don't have to do any computation. So if I have a magnetic dipole in presence of a magnetic field, what is the Hamiltonian? Sorry? Speak loudly, I mean. Yeah. Electrodynamics. Mu dot B, good. So my Hamiltonian is minus, okay, forget about the minus sign, it's some proportional, let's be accurate. Minus mu dot B. What is mu in terms of spin? You don't worry about, take mass to be 1. I am not worried about anything else. Sorry? Good. So mu is q times spin. Now, is it clear what is happening here? What is mu1 then? It's E times S1. And what is for this? Good. So the next term that you would expect is S dagger S1 minus S2 dot B. Just basically follows from this term. Okay. So my mu1 is proportional to E times S1. Mu2 is proportional to minus E times S2. I just use that expression, write my form 1 over m that we know from HQET and NRQCD and everywhere. So this is something you can literally derive explicitly, but we kind of bypass through a short way. So if there was 2 electrons, I would get S1 plus S2. If I had E plus or E minus, I would get S1 plus S2. I'm not talking about bound state there, but okay, let's say. But if I had E plus E minus, I would get S1 minus S2. Okay, so my PNRQCD Lagrangian or PNRQED is S dagger I del 0 minus, you would get one of the kinetic terms as del R square by 2m. S, let me just maybe carefully take it. Yeah, plus del R square by m. There are other terms in the M expansion, minus V, which depends on R, also depends on momentum, sigma 1, sigma 2, the spins. I'm just writing a generic form, so details are in a paper that if anybody is interested, I will let you know. Plus S dagger, sigma, R dot E, S plus 1 over M, S dagger, S1 minus S2 dot B, S. So this is my PNRQED Lagrangian, okay? And if I take the leading order equation, I immediately get Schrodinger equations. So if I know the potential, I will solve Schrodinger equation, I get the positonium energy levels. That's the main thing. So let me show you one very, okay, so the next question is, this is very naive. So in QED, we don't have color. In QCD, let's say quark, anti-quark, what color degrees of freedom will come up? If I'm talking about, let's say, a charm, anti-charm system, bottom, anti-bottom system, what are the degrees of freedom that I will have in terms of paired field? Think of in terms of paired field. So just like there I defined this phi, think of in terms of paired field. Yeah, I just want the quantum numbers. What is the color of charm, anti-charm, which is 3 times 3 bar? What are the 2 colors that comes out? Yeah, so singlet and octet. So in QCD, I would have a singlet field and an octet field. There would be a Lagrangian for the singlet, there would be a Lagrangian for the octet. You just have to, okay, this would be maybe a little tough, but just to note that terms like these won't come up where there's a singlet transitions in QCD, because in in QCD, because of this color degree of freedom, that there would be a trace and that such type of singlet-ringlet terms would be 0. But singlet to octet transitions, so where I have S dagger R dot E A with octet A, these type of terms can come up. And terms like these are not allowed. Just for them. Exactly, chromoelectric field, chromomagnetic. Except the Lagrangian is more complicated. You have octet degree of freedom, you have singlet, you have these mixed interaction between singlet octet. You have octet-octet dipole, you have octet-octet magnetic dipole, singlet-octet magnetic dipole, and so on. Okay. So that is where I will stop. I mean, I don't want to dwell. But let me show a very...
0 and spin 1.
Yeah, you can express again the singlet in terms of spin 0 and spin 1, and again rewrite everything in terms of...
Spin 1.
Exactly. That will all come up. I mean, if you are doing spin average, then you generally don't do that. But if you have to do some spin interaction or spin coupling, then you really break it in terms of spin 1, spin 0, octet also in spin 0, spin. You won't see color octet quarkonium, but you would see a hybrid, which is color octet quarkonium plus a gluon. Soft gluon, yeah, soft. All these tetraquark states are color octet UQ bar with light quark. So there is implications that we see. Yeah. So when we write, so in things like hybrids or tetraquark, it's not like JSI. Yes, JSI has a small size. And so singlet octet makes more sense there. Now, states like tetraquark, pentaquark, hybrid, they are bigger objects than quarkonium. So you really have to put lambda QCD at some soft scale, and then you have to integrate out lambda QCD. Because we have to integrate lambda QCD, we write everything in terms of hadronic degrees. But eventually singlet octet enters when you try to express these potential. The potential that I wrote here, the form of the potential will capture the short distance and long distance physics. That is, at short distance, I would have the singlet octet business. Okay, so we have studied this scattering in electromagnetism, which is basically scattering of low energy photons on atoms. And this is what explains why we see the sky as blue. So I have, let's say, a light source coming in. There is an atom here. I have an isotropic scattering, and then let's say somebody is standing here and there is this observation happening. So my photon, which is scattering of this atom here, is less than m alpha square, which is less than m alpha, which is less than m. I don't want to polarize my atom. I don't want to ionize my atom. Basically, it's low energy scattering that I'm looking at, even low energy than the PNR QED scales. And so such type of terms, so I can define a new EFT. So let us call this new EFT, where I have atom fields, but on that, in order to make the Lagrangian, I have terms like E square plus B square plus, so this is my Lagrangian here, plus some pi dagger n I del 0 minus En plus del R square over M I n. So this Lagrangian is describing an atom with quantum number n. So this is atom field with quantum number n. And these are the Wilson coefficients that we need to determine. So the full theory is PNR QED. Exactly. This is the point. So in PNRQED, which you just saw, the diagrams that will contribute is, so let us talk about R dot E, and these will be matched to E square. Is everybody following? Where is the electric field coming from in PNRQED Lagrangian? It's this term. Yes? So I basically put the light, the photon just creates a dipole, the dipole interacts, and then the photon is emitted, and I regain back my atom back. So that's the idea, basically. So exactly, this is the point. Yeah, so writing, okay, so let me do it in this way. So I have an atom state n. I started with an atom state with quantum number n. I want to end up with an atom state in the same quantum number because I'm just doing a scattering problem. So I have, just let me write. So Ri, this is my propagator, E minus, so HS0, H is basically this part. I mean, this is my interaction term. This is my H, okay? RJ. Am I correct? Yeah. EI, EJ. And then I'll come to it. Just let me finish it. So then I use the isotropic condition that this is proportional to E square delta IJ over 3 for D equals to 3. And so on the left-hand side, what I have is N, sorry. So on the left-hand side, what I have is N R dot 1 by E minus HS0 R E square times minus E square by 3. So these are factors of E sitting here that I have not accounted for properly. Now to make sense of this, you have to introduce complete set of states for the Hamiltonian. So you do that, and what one get is something like dot. N alpha by 3, 4 pi alpha by 3, which is E square, which is equals to DE E square. So basically this intermediate state is summing up all the quantum numbers out, except my initial state. Another reason is that this is 0, because let's say I started with some angular momentum 1 algebra and angular. Exactly. Exactly. So, and using the fact that, so I sum up all state except the n. And that uses the fact that this is 0, because if you are starting with some, let's say, S wave state, this will introduce 1 unit of angular momentum, and so this matrix element has to be forced to 0. That's the argument, basically. It's everybody followed? Yes? So this is 0 by angular momentum. Sorry?
problem occurs when n equals m.
Yeah.
And that is prohibited by
Angular momentum algebra. Symmetry is already prohibiting the system. Okay. The symmetry is already, angular momentum symmetry is already telling you that that cannot appear. Yeah. HMN is equals to 0. And so you see, I immediately get a DE, which is this, let me just write and show you the scaling. So 4 pi alpha. Again, the factors of minus are flying around. So I'm sorry, but it will be in the notes. So you can keep track of it. So let us do the power counting of this because that to give us some idea. So there is already a power of alpha. How does R scale like? Good. So I have two powers of R. And this energy is this. Yes? So really what you are getting is M alpha cube. Okay? I mean, I have M cube, alpha is cancelling one of them, I have alpha cube. Now in atoms, what is the natural length scale? Sorry? Yes, good. So this is related to Bohr radius. Bohr radius is 1 by M alpha. You can go and check in Wikipedia, this is 1 by M alpha. So really the DE is proportional to Bohr radius cube. If you do the analogous calculation, which I leave it as an exercise for you to figure out, where I have sigma dot B over M, which is, yeah, there is time? Yeah. So you should tell me what is the dB that you get, or how does dB scales? You don't need to do all of this calculation. There is directly, I wrote everything. You should see and put in what is the dB that you will get. So question is, yeah, how does dB scale with M alpha, or what's the thing? What's the result? Look at the two vertex of electric and magnetic field and see what's the difference between the electric vertex and the magnetic vertex? And, sorry? 1 over M, there is no alpha, okay, 1 over M. If I trace back all the steps, which places, so I wrote this expression here, what will change? This, good. And what will come, very good. So the dB, I will still have some power of alpha here in the front, 1 by M square, 1 by M alpha square, which is really, yeah. No, the R dot E will not have 1 over M. Yeah. Yeah, it's a gradient. It's coming from the gradient term. Just let me check. Yeah, correct. Okay, everybody followed? Because it's coming from 2 powers of E. I mean, the magnetic dipole is E times sigma dot B, yes? So it's E square will give me an alpha. Question? No. So this is basically telling you that dB by dE is alpha square, which means dB is much less than dE. to the scattering cross sections at leading order in alpha, I won't have any magnetic polarizability. I mean, I won't be sensitive to magnetic polarizability. The polarization or the scattering is going to happen through electric dipole. That's the main thing in the Rayleigh scattering. And so once you have all of this machinery, what is the unit of cross section? So let's write the cross section. What is the unit of cross section? Length square. What are the length scales now I have, or what are the energy scales that are coming up? I have a photon of energy, and I have this dE. So now think of in terms of this way, my amplitude will be just given by this dE parameter. So I have E gamma. And what is the other scale? So the scattering is only happening through elect dipole. Yeah. E square dE square, okay, which is E gamma 4 A0 6. Yeah. Did people follow the last line? My only length scale in this scattering problem is the photon energy and this A naught, which is proportional to dE, or some power of A naught that is related to dE. The scattering is only happening through electric dipole, and therefore, let's not worry about some factors of 2, 3, 4 in front. This would be the cross section. So I construct out of E gamma and dE what are the units of sigma. And so this is the only piece that would be existing just from the dimensional units. And that directly gives you this relation. So what does this tell me? Yes, exactly. So this is basically telling you blue light scatters more compared to red light. Yeah, I think violet will be scattered more, but we are not sensitive to violet and indigo. So that's why we see why sky is blue. So this is, as you see, is the power of, in a way, of PNR-QED really. I mean, yeah.
You were writing over there.
A naught times A naught.
Is the like M alpha square, M alpha.
Yeah.
Right. So there are many lengths scale.
Yeah. Okay.
Here you have derived that it is proportional to n, and then it follows.
Yes.
But in typical text,
no, I agree.
Yes.
Yeah. Yeah. You. Yeah.
Then it has to be enough.
Yeah.
Deriving.
Yeah.
Not wiggling your hand.
Yes. So
Not as easy as
yeah.
some people there.
No, I agree. So this is the most simplest example that I can tell you for PNR-QED. The most complicated one is lamp shift calculations. And that's, I would say, beyond this class because it will already take 2-3 hours to do it. Yeah, people have used PNR-QED to compute lamp shift calculations up to like order m raised to alpha 6, I think, right now. And it's very nasty. I mean, the calculation is really nasty. And we consistently use, like people in atomic physics are now using PNR-QED to study scattering of atoms with lasers. There is a very nice paper by a group at Ulm. If somebody is interested, then I will share the paper. But yeah, we use, for QCD, we use the PNR-QCD, which we didn't go much detail except some few comments. Thank you.